Hey guys, welcome to another video. Today we're going to be going through the second part of forces. It's a big topic. We covered approximately half of it the previous video, so we're going to be aimed to cover the rest today. Now, the first concept is force and acceleration, and the most important thing you have to understand here is that any net force on an object is going to cause acceleration. Remember, acceleration, velocity, and things of that nature, they're all vector quantities. Remember the difference between scalar and vector? Well, remember, vector quantities has both the magnitude and it's got the direction. Whereas scalar quantities only have magnitude. So we're talking things like speed is an example of a scalar quantity, and velocity is an example of a vector quantity, and so is acceleration, because acceleration, remember, is as a result of velocity, and so therefore these two are strongly linked together. And now we're going to be adding force to the equation here. And the main equation is going to be, and you'll come across this equation a lot, it's a very important one that you have to use a lot in this course, is force equals ma. And so force equals mass times acceleration. And because acceleration is a vector quantity, so will be force, as I've mentioned before. The units, of course, will be force in newtons, mass in kilograms, and acceleration in meters per second Okay, so here's the formula that I just outlined. Force equals mass times acceleration. Now, the resultant force of acting on an object is quite simple to calculate, and so basically the thing you have to understand is if the forces are acting in the same direction, then you simply have to add it up, right? And that makes sense. So 5 newtons to the right here on this top example, 3 newtons to the right, and so the resultant force is going to be 5 plus 3, which is 8 newtons. Pretty simple. But if the force is going in the opposite direction, as you might expect, you're going to have to subtract the forces, and of course the stronger force, that's where the object is going to have the resultant force at. So for example, we've got 20 newtons to the left here, 10 newtons to the right, and so what will happen is the resultant force will be 10 newtons to the left, because obviously the left hand side has the stronger force. So the direction will head that way, and the magnitude of it will be the difference between the right and left, which is 20 minus 10, which is 10 newtons. So that should make fairly simple sense. So the main takeaway here is that any net force should result in some sort of acceleration, okay? And remember, acceleration is a vector quantity. Now, imagine a car that is traveling at a constant speed of, let's just say, 60 kilometers per second, okay? So we've got just clear the board here. So let's just imagine this car here that is traveling at 60 kilometers per hour. Something like that. And so as the car travels at 60 kilometers an hour at constant speed, is this car accelerating or not accelerating? Well, it's not accelerating, right? Because acceleration is a change in the velocity of the car. Now, let's imagine the car goes through a roundabout, and you know, I don't know if you have roundabouts in your country, but it's basically this circular little thing where cars can sort of travel around, okay? So imagine now that the car is traveling around this roundabout in a circular motion at 60 kilometers an hour. Now, the question is this car accelerating? The answer is yes, it is accelerating. Why? Because although the speed at 60 kilometers per hour is exactly the same, it's constantly changing its direction as it moves around this circular pattern. So what it means is anything that is traveling in a circular motion, although it might have the constant speed of, imagine, 60 kilometers an hour, because it's traveling in a circular motion and every split second along the way, it is actually changing its direction. And remember, acceleration is a vector quantity. So it's got speed, which is the magnitude, but it's also got the direction. And in this example that I just talked about, although the speed is constant, the direction is constantly changing, and therefore the object by definition is accelerating when it goes in this circular pattern. And so that's what we're going to be talking about in this second part of the slide, where we talk about centripetal force, which is basically the force that causes any object to move in a circular pattern. And the main thing to take away here is that the centripetal force is always going to act at right angles to the direction of the movement of the object. And so you might be able to figure out in this diagram to the right here, you've got the centripetal force sort of directing, or in the direction of the center of the circle, where the velocity or the sort of direction of the object itself is going at 90 degrees to that force. And the setup is exactly what you need for an object to move in this orbital pathway, this circular pathway. Okay, so therefore, if we take a look at a circular object, or an object moving in a circular pattern, I should say, something like that. This blue thing is the object. What you'll find is that towards the center of the object, you're going to have, again, the centripetal force, which is always going to act at what angle? The right angle to the direction of object. And when you've got this set up, then the object will always move in a circular pathway, as you can see here. And so this right angle thing is very important. You need to be aware of that, and you also need to be aware of the fact that the object is indeed accelerating, even though the speed of the object may be constant. Now, you have various ways of increasing the centripetal force, which you can determine that with a few factors. Number one, if the mass of the object increases, then you'll increase the centripetal force. If the speed of the object increases, you'll also increase the centripetal force. And if the radius of the circle decreases, again, you're going to increase the centripetal force. So there's fewer factors that can affect the magnitude of that. Now, friction and air resistance. Friction is a force that occurs between two surfaces that impedes the motion and results in heating. So the fact that you can pick up a book, the fact that you can walk on the floor, the fact that you can do anything on this world is actually as a result of friction. Imagine if you didn't have any friction between two different surfaces, then there's absolutely no way that anything would work. For example, the wheels on a car occurs by friction because of the fact that the tires are having a constant grip on the surface of the floor, and that allows the car to move as the engine starts to turn the wheels, etc. And so friction is important. Now, air resistance is actually a type of friction. So basically, when you're free falling through the air, what's going to happen is that the air molecules inside the air it's going to start to create some friction against your falling body, and what that will do is create an upwards force as a result of that friction. So for example, if you've got yourself falling, and there we go, you're falling down, and you've got the force of gravity that's pulling you down, right? Well, as you fall down, the air molecules they're gonna start to hit your body, right? As you fall down, the air molecules will start to sort of collide against the structure of your body, and what that will do is eventually cause an upward force called air resistance, which is really just friction. And the air resistance, you're going to start to build up the force, and eventually what will happen is the force of gravity is going to equate to the force of air resistance, and so you're going to start to find that you don't have any resultant force. Initially, this downwards force is going to be greater than air resistance, which is why you fall in the first place, which is why you accelerate downwards. But eventually, as the force of air resistance starts to build up as you fall, when you find that the force of gravity equals the force of air resistance, in other words, the downward force is equal to the upwards force, then remember, when forces act in opposite directions, you have to subtract to find the resultant force, right? If these two forces, downwards and upwards, is completely equal, then you have no resultant force. Resultant force equals 0, and what that means is you, the free falling object, is going to stop accelerating. Your speed is not going to increase any further than that, and when that happens, we call that terminal velocity. Okay, so basically that sums up friction and air resistance. Now, we're going to take a look at this thing called a moment, and it's all about the turning effects of objects, right? So the moment of a force about a pivot is equal to the force multiplied by the perpendicular distance from the pivot point. And you can see how this works here. You've got the pivot, which is the little thing that the object is sort of lying on, and so if you've got the pivot point there, then the rotation is going to be present from that point onwards, right? Like the object can either rotate clockwise from that pivot point, or it can, rotate anti-clockwise from the pivot point. But how the object rotates is going to be dependent on two things. One, the force acting on one side of the pivot, and also the distance from which the force acts from the pivot point. And so what we have to calculate when we're doing these things is, well, okay, how much clockwise moment is there, and how much anti-clockwise moment is there, and what outweighs the other? Okay, so if the anti-clockwise moment is greater than the clockwise moment, then the object is going to turn anti-clockwise, and it's going to be the same vice versa. Okay, so basically, whatever moment is greater will take over. Now, obviously, if the anti-clockwise moment and the clockwise moment is exactly the same, then you've got what we call an equilibrium, where you don't have any resultant moment, and therefore there's going to be no turn on the object. So let's take a look at a few of these examples in a second. So, for example, this first example here, what you can see is that the clockwise moment is what? Well, look at the direction of the forces here. This, on the right hand side here, the force is going upwards, right? So it's sort of turning the object in what way? It's turning it anti-clockwise, right? Because if you take a look at, if you imagine pulling this right-hand side upwards, then the entire object is rotating anti-clockwise in reference to the pivot, yeah? Whereas this left-hand side, if you just think about it logically, if you just imagine pulling up this end here, then you're turning it clockwise. So let's take a look at the clockwise moment. Remember it being force multiplied by the distance away from the pivot. So we've got 2 newtons times 3 meters, you've got 6 newton meters. The anti-clockwise moment, which is the right hand side here, you've got 1 newton times 10, which is 10 newton meters. So the net moment is whichever is bigger. So we've got the anti-clockwise moment being 10 and the clockwise moment being 6. So therefore you've got a resultant net moment of 4 newton meter towards the anti-clockwise direction. Okay, so hopefully that makes sense. What about this bottom one here? Same thing. What is the clockwise moment? Well, we've got 20 multiplied by 2. We've got 40 newton meters, whereas we've got 10 multiplied by 1 newtons for the anti-clockwise moment. So the resultant moment this time round is going to be 30 newton meter clockwise, because this side has a greater, the greater magnitude. And lastly, again, clockwise moment will be 2 newtons times 3, giving you 6 newton meters, whereas we've got on the right hand side, which is the anti-clockwise moment, we've got 6 meters times 1 newton, which is 6 newton meters. So in this case, there's no resultant moment as a result of the fact that the clockwise moment is equal to the anti-clockwise moment, which means that this setup is in equilibrium, meaning you won't find any rotation. So let's talk about the center of mass of objects. Okay, the center of mass is pretty much the point on an object where the overall mass can be considered to be concentrated, and hence where the weight of the object is considered to act. So, you know, if you've got an object, let's just say, you've got an object like this, right? Now, obviously, this object is going to have atoms and matter, and the matter is going to be scattered all over the place, and, you know, each particle is going to have mass. So, you know, technically speaking, the weight will be distributed equally throughout the entire, you know, depending on where the particles lie. But basically, what the center of mass is that we're just gonna consider that the mass is concentrated in just one point in the object, okay? Just to make calculations and stuff more simple. So, get rid of that. So, we're gonna consider this point to be exactly where all the mass of the entire object is concentrated, so that when we take a look at things like you know, the weight, which is basically the force on the weight, we can just extrapolate it from this point and say, well, look, you know, this is where exactly the mass is concentrated, and that's exactly where the force of gravity will act. And so we've got the downwards force of weight occurring at that particular point on the object. So the center of mass of a plane laminar can be determined with a fairly simple experiment. When we take a look at experimentally figuring out where the center of mass might be, this is how we do it. We put a pin through a point near the edge of the laminar. It doesn't matter where, just put a point, right? Put a pin through it. And you're going to allow this laminar to swing freely until it eventually comes to a standstill. And from that point onwards, you're going to make a vertical line from the point where you put the pin through the laminar, okay? You're going to mark that vertical line, and what you're going to do the next time is you're going to put a pin through another point on the laminar, and we're going to go through the orange point this time, right? So if you made the black, you made the line, now you go do the orange, and again, you do the same thing, you just put a vertical line after the laminar has come to a standstill. And so what you'll now find is that you've got two vertical lines, each extrapolated from the points of the pin that you've put through the laminar, and the point at which those two vertical lines cross is called the center of mass. Okay, so that's how you figure it out. So the center of mass is very important when we consider the stability of an object, which is, how easily is this object going to topple or fall, right? And the stability of an object is determined by the center of mass and where it lies on the object. So the object is stable if its weight, which is the force of gravity acting on the center of mass, is inside the base of the object. The object will tip over inevitably when the weight falls outside of the base of the object. And so you can think about this from a conceptual basis, right? Where if you've got an object that sort of looks like this. Just by looking at it, you can see that this object looks pretty stable. Now, it's looks like a coat hanger, so I'm just going to make it 3D here. By nature, this looks pretty stable. And the reason it's stable is because if you consider the center of mass, let's just say right here, right? The force of gravity acts downwards like this. Clearly you can see that the force or the weight of gravity acts within the base of the object, okay? Now, if you think about objects that are a bit more unstable or easy to fall, you'd think of objects maybe something like this, okay? Like something like this, right? And so, consider the force or the center of mass, maybe somewhere like that or something like that, and you've got the force acting down. Now, it's still within the base, but you can see that it's certainly not as stable as the one on the left. And so what will happen when the force of gravity exists outside of the base is when basically the object is going to fall. So, for example, if we had another object that sort of just maybe just looked like, I'll use a different pen. I have no idea what I'm drawing, but maybe something like this, an object that looks like this. And we're just going to consider the force of gravity acting at maybe this point here. We're going to call this the center of mass, and the force acts downwards. You can clearly see that it's outside of the base, and when that happens, you're going to find that definitely it's going to fall downwards. The object's going to fall, okay? So the object isn't stable. And this example here is just another one of those where clearly if the force of gravity is acting within the base, it's stable. If it's not, then it's unstable and the object is going to fall. So we talked a little bit about vectors and scalars in the beginning of the video. So vector quantities have a magnitude and a direction, whereas scalar quantity only have magnitude. So when you have two vector quantities together, you can actually figure out what the resultant vector would be with a scale diagram, which is basically where you plot everything, not necessarily plot, but you redraw the setup with a specified ratio and in correct proportions on a piece of paper, and you measure everything accurately with a protractor and a ruler in order to find the resultant vector, and we'll figure out how to do that in a second. But the main idea is for you to choose a scale. So if we wanted to figure out this, a good scale might be 1 centimeter equals 1 Newton, so that if you were to draw out the 6 Newton force, then you just draw it at a length of 6 centimeters, and the 8 Newton, of course, that would be 8 centimeters. You do actually need a little bit more information here. So imagine this is parallel to the ground. We're going to call this angle 30 degrees, and we're going to call this angle 50 degrees, okay? So now that you've got all the angles, the idea is to choose a scale, and as I said, 1 Newton per 1 centimeter would do fine here. You can redraw the diagram on paper with the appropriate lengths and angles, and then you're going to rearrange that, but I'll show you how it's done here. So I'm going to take you to the whiteboard. Now the first Okay, we're gonna keep this zoom at 100%. Well, let's just go. We'll go 182%. Because we do need to keep it consistent. But we're just gonna draw the first force, which remember was at a 30-degree angle. So we're gonna draw that, and we're just gonna, if you take a look closely at the ruler, you can see that it's got markings, right? So I'm gonna start with this marking here, and as with a normal ruler, we'll just call from this spot to this spot 1 centimeter. Okay, so we're gonna go 1, 2, 3, 4, 5, and 6. That's exactly 6 centimeters, right? And I'll draw an arrow pointing here. That's 6 centimeters, and we're gonna rotate that because we know that these ones are 100 degrees apart, which means I need to set it to 40, and I'm just gonna draw the second force. As before, we're gonna measure this carefully. So we've got 1, 2, 3, 4, 5, 6, 7, 8. That's exactly 8 centimeters. Slightly more, but we'll forgive ourselves there. So that's generally the setup that we're going for. So that's carefully measured. This red one is 8 centimeters and the green one is 6 centimeters, which corresponds to the units of 6 newtons and 8 newtons for each of those. So now what you want to do, once you've redrawn that setup and with the appropriate angles, etc., is to rearrange it so that you've got the nose of one arrowhead pointing to the tail of the other. So for example, you can do this, and you can sort of pop it like that, right? Or you could move that back, and you could possibly just adjust this one over here, and oops, didn't capture that correctly, and you could possibly just move it like so. What you do is completely up to you. Both methods will work. So I'm just gonna leave it like that, where I've adjusted the green arrow and I've adjusted it on a nose to tail basis, so that the nose of the red is pointing to the tail of the other. But again, you could have just as well done the red and moved the red away, so that the red tail is sort of connecting to the head of the green. That's, as I said, it doesn't matter. But what matters now is when you calculate the resultant force, the idea is for you to draw the line connecting the tail of the first force to the arrowhead of the second force. So in this case, we're looking at something like this, right? We just want to connect it. And so we've got the blue marker denoting the resultant force, which will connect like so. So that's the resultant force. The direction you can calculate by measuring it with a protractor, and I already know it's 84 degrees because that's what my ruler here is saying. But in terms of the magnitude, all you have to do is just measure it. And if you take a look, considering this is 0, we've got 1, 2, 3, 4, 5, 6, 7, 8, and 8.2. 2 centimeters. And so 8.2 centimeters will equate to 8.2 newtons on our scale. So that's a way that you might be able to do that. So that's sort of how it's done. At the time of this PowerPoint slide, I just assumed, for example, you might measure 12 centimeters, and so if that's the case, then obviously the resultant force would be 12 newtons. But as you can see, when you properly do it and you measure everything out, then for this particular example, you'll get 8.2 newtons. Okay? So I hope that made sense. In the next video, we're going to be covering momentum, work, and energy, and things of that nature. So I hope you found this video useful. If there's any questions, feel free to comment below. For those of you that are taking other subjects like chemistry and biology, make sure you check my Patreon channel out. I've got a lot of other resources, mainly past paper-based resources that can be quite helpful for your examinations. We'll be posting some physics ones as well eventually, but I just want to get through the course here on YouTube first before I go ahead with that, but it will be out at some point. So thank you very much, guys, and I will see you in the next video.